Thanks so much, Barry. So today I'm going to be presenting with Yi and Stephen on various projects we have to implement cryptographic primitives in SNARKs, specifically in Circom for Groth16. Stephen unfortunately couldn't be here today for COVID-related reasons, so he has a recording that he's been kind enough to share with us about Double Blind, which is an RSA Circom project and an associated set of tools and demos. Cool, so let's get started. The first question here is why bother? There's a bunch of questions around why even do this. As we are moving away from Groth16 and as we are moving towards more SNARK-friendly cryptographic functions, it seems like this is sort of, an attempt to live in the past. But, there's a number of important reasons why this kind of stuff is important. The first reason I would say is that today with SNARKs, and this isn't something that's necessarily specific to which proving system we're using or what cryptographic primitives we're implementing, one of the key sort of framings that we have around what SNARKs enable us to do is that they give us an expressive language for claims. So what does that actually mean? Well, we see ZK SNARKs very much as something that falls under this category of quote-unquote programmable cryptography, i.e. tools that turn math problems into programming tasks. Rather than having to use special purpose-built cryptographic tools, we now have these programming languages that allow us to define circuits, compose arbitrary claims and primitives together, things like, I know a secret that is behind one of these commitments or behind this particular commitment or which has certain guarantees around certain commitments. And instead of needing to go to a cryptographer and ask them to build a new special purpose math protocol for us, we can instead write circuit code. So here's one example. Membership proofs we're finding are likely to be increasingly important as we move towards a lot of these new ZK-enabled apps. And to give an example of the flexibility that SNARKs provide over previous primitives that we've had for membership proofs, I'm going to present a series of claims. So the first claim, and one that has underlied a lot of internet infrastructure for many decades now, is the simple claim, I know a private key corresponding to Alice's public key. We have protocols that do this quite well. We have key registries that a lot of people are now on. And this is something that's been around for a while, and it's been very useful. And it's something that we're very well equipped to do prior to these sorts of programmable cryptography tools such as SNARKs. Okay, so a slightly harder claim is the claim, I know a private key corresponding to Alice, Bob, or Charlie's public keys. This is something that is sometimes known as a group signature or a ring signature. And while protocols for proving claims like this have existed for a while, it unfortunately is the case that oftentimes they're not super compatible with the protocols and registries we have for people to make this kind of claim, meaning that you aren't able to move between these two claims in the same system. You need to bootstrap an entirely new identity registry, an entirely new infrastructure in order to be able to have a system that allows you to make both of these types of claims. In a SNARK, however, this turns out to be really simple. If you've got the cryptographic primitives implemented for this inside of a SNARK, you can simply write a circuit that asserts that I'm going to make a commitment that is equal to a key generation function evaluated on a secret. That commitment, when compared against the set of commitments that I want to prove that I know one of the secrets to, via this polynomial evaluates to 0. And then I can generate message attestations that might bind me to all sorts of things. Okay, slightly harder than this is I know a private key corresponding to Alice, Bob, or Charlie's public keys, and depending on some, perhaps configuration flag or some, in-protocol configuration, the other two who did not sign this either can or cannot disavow this message. So once we get into this territory, we see things like, there's all sorts of papers that propose different mathematical schemes for group or ring-like signatures that allow you to either post facto prove that you did or didn't sign the message. With SNARKs, however, this is super easy. You can simply, take this circuit pseudocode and do things like add assault. So that way it's very hard to deny that you don't know some salt, which would, when combined with your private key, generates the message attestation. And then we get to more elaborate claims like this. I know a private key corresponding to Alice, Bob, or Charlie's public key, and I either possess a signed attestation from one of David, Eve, or Fred, these identity attesters who are trusted, or during the block with header X, I knew the private key corresponding to an account with at least 32 ETH, and you know, you can imagine like a bunch more predicates like this. So once we get into this kind of territory, we now clearly need kind of an expressive language for these sorts of claims. We can't rely on going to a cryptographer and asking, hey, can I get a zero-knowledge protocol for this? That's something that is simply not feasible. And again, it's ideal if the protocols or strategies that we have for making these, or for proving these kinds of claims are also allowing us to live in the same system with the same key registries where I'm making these kinds of claims as well. Okay, so the second reason to specifically implement these existing primitives like ECDSA or standard hash functions into ZK snarks is so that we can bootstrap off of existing data sets. So I want to kind of illustrate the dichotomy here between two ideas. There's the idea of snark-friendly cryptographic primitives, and then there's the idea of snark-compatible cryptographic primitives. At least in the near term, our most widely used cryptographic systems will not be snark-friendly. By snark-friendly, what I basically mean is, things like commitment schemes or signature schemes or things like that that are specifically very performant to implement inside of a snark. Existing data sets oftentimes rely on cryptography, which was built out before snark constructions were even known. And so at least for the foreseeable future, if we want to use like existing identity registries or other data inside snarks, inside our expressive identity language, we're simply going to need to do the hard work of implementing these primitives inside of snarks. So for example, when we speak about like key distribution or identity registries like GPG or SSH, we have these like large, basically, registries of things like RSA keys that now exist out in the wild that we could be making claims about if we can get those into snarks. And there's been a lot of, there's some overlap as well here with folks working on ZK EVM related work, where we're also interested in implementing ECDSA keys ECDSA algorithms inside of snarks because that would enable us to make these expressive claims about on-chain data and about on-chain identity sets. So yeah, snark-friendly might mean that this particular primitive is very performant inside of a snark, but at the very least we can kind of aim for primitives that are commonly used today, making them snark compatible by building out a standard set or a nice and optimized and easy to use set of libraries. And once we've done that, we can see what applications we can build. Okay, so a few more notes on our approach in general, how we're thinking about where these primitives fit into a larger context and why we implement them in Circom and with Groth 16. So there's a couple of things that we aim to do at Xerox PARC and with this particular primitives implementation project. So the first thing that we always do is we try to target useful end user-facing applications. So, for example, many of the applications you saw yesterday, such as stealth drop, private airdrops, these are things that can be concretely useful to users, you can imagine even as early as today. Double blind, which allows for RSA group signatures as well, could allow you to build message boards within a GitHub organization, and that's a concrete use case you can imagine today. So we target an end user-facing application, and then we actually try to build it out end to end. And what we found is that currently the tool stack that has that's kind of the most stable and the most easy to use end to end, all the way to the point of having a user in browser being able to generate a proof and participate in the protocol is Circom and Snark.js. And we do additional work like what Lakshman and Uma were talking about yesterday with MetaMask snaps to really try to close the gap between these ideas being these theoretically interesting ideas and these actual proof of concept prototypes you can physically play with. The other thing that we focus around is just get something working to begin with and then optimize. So some of the circuits we'll show today are like super expensive and can only be basically, proofs can only be generated on a dedicated proving server. But we're okay with this for now, and we're okay with sort of having these like shadow like backends, because we anticipate that as we move to better proving systems, or as we continue to optimize circuits, or as libraries get better, or eventually as hardware gets better, like this will be a very solvable problem. I think even with like Circom and Snark.js, like 3 years ago, the like performance accessible to your average ZK developer was probably like 2 orders of magnitude worse. So you can kind of imagine that things are going to keep getting better. And then along the way, in actually holding ourselves to implementing an end user facing application end to end, we're going to uncover engineering and design challenges. So for example, like this is what motivated the MetaMask snaps work. This is what motivated Nalin and Blaine and Kevin's work on like chunked Z keys. It's something that makes things like delegated proving really exciting. And yeah. So we aim to make existing cryptography at least Snark compatible to see what can be built. And in doing so, we can create this feedback loop between applications and infrastructure, so we can understand like what really are the next bottlenecks to Snark apps getting into production. Okay, so first I'm going to talk a little bit about Circom ECDSA, which is a set of circuits that we published and have been optimizing for the last couple of months. So the idea here is we basically want to implement ECDSA key generation and signature verification in Snarks. And currently, we have a prove-to-pub circuit that takes a private key and proves that it takes a secret private key and proves that it is the preimage of the ECDSA pub key gen function. And that works in under 100K constraints. And we also have ECDSA signature verification in 1.5 million constraints, and you can check out those circuits as well as a number of useful utilities and demos on our Circom ECDSA library on Xerox Park GitHub organization. One thing I'll note is that these circuits are certainly not production grade. They haven't been audited. They haven't been, we haven't really been able to run like verification tools on them. So this is very experimental, and again, like the goal here is proof of concept applications, not necessarily, I don't think these are fit for production, or there will be at least like a number of pretty substantial additional steps we'll need to take. Here are some benchmarks. You can see that the pub key gen function, or the pub key gen circuit, is 95K Groth 16 constraints, and unfortunately the proving keys are pretty big. So that's another kind of one of the limitations to putting these into apps, but we have a number of workarounds for this kind of stuff. A few of the challenges that we encountered in implementing ECDSA was, the first thing was we had to build out a pretty robust set of big-int arithmetic techniques. We do slightly different techniques from what Aztec and, as I'm aware, like a few of the other teams are doing for their big-int implementations. We also do a number of curve-specific optimizations around the fact that we're working with the SecP 256K1 curve, where the underlying field is very close to 2 to the 256. There's a couple of subtleties with ECDSA, and then one of the next things that's really important here is figuring out like audits, or ideally some sort of like verification of correctness of at least different subcomponents of these circuits. So we're going to be, me and Yi will be speaking about this in an afternoon workshop at 1:30 if you want to come and learn about some of the trickier like optimization techniques that we are using. And hopefully some of them may also be applicable to Plonk-like systems. Yeah, so a couple of applications. We saw Stealth Drop yesterday, which allows you to do airdrops that, to addresses that can't be linked to the original address in the whitelisted set. Additionally, you could imagine like things like message boards, and we have, this is a ZK message board. It's not one with ECDSA integrated into it, but it sort of demonstrates how one might build an anonymous message board that allows you to prove membership in a group. And you can imagine like on-chain identity sets with either ZK attester or some other infrastructure that allows you to construct sets and make claims such as I held X tokens, at least X tokens at Y time, or like I am the owner of one of this NFT collection set, things like that. Okay, so next we're going to show Double Blind, which is a project from Steven, who couldn't be here today, so we have a video from him.
Hey everyone, today I'm going to show you an application we built called Double Blind. Double Blind is an off-chain application that allows anyone with an RSA key to anonymously sign messages on behalf of a group. Let me show you how it works. First, let's open up the page and type a message. Does anyone else think we should switch to 3-space indentation? This is a potentially controversial message, and it's the message we're going to anonymously sign today. To do that, we need to define the group that we are signing on behalf of by listing the group public keys. So let's include our friend Vitalik, whose public key I have pulled up, and also ourselves, because we need to do that to be able to sign as this group. Finally, let's enable the secret identity feature. This gives us a masked identity, which is like a username of an anonymous account that we control and post under. This will be important later on if we want to prove that we were the author of this message or link multiple of our messages together. We're now ready to generate the group signature. When I click the sign button, the application starts computing a zero-knowledge proof using the Snark.js library. The ZK Snark proof is computed by evaluating a custom Circom circuit that verifies the constraints for authentication and authorization, while keeping my identity and secret keys private. It usually takes around 30 seconds and results in a succinct string that is easily shareable. Here's the string. Now I'm going to take a brief detour from the demo to explain how the circuit works. First, the circuit authorizes me to sign for the group by validating that my public RSA key is included in the list of authorized keys. This validation is done by checking a Merkle inclusion proof, that my public key is a leaf of a given Merkle root. While the Merkle root is treated as a public input, the Merkle proof itself and my public key are private to preserve anonymity. In parallel, the circuit authenticates me by verifying a signature that was generated using my private RSA key. This is what we call the double blind key, and it's sufficient to act as my login credentials. The signature was generated using this terminal command I'm highlighting and entered into the app via this text box. Note that I never needed to paste my RSA private key into the application. This is consistent with best practices for safely handling private keys. The signature is another input to the circuit, but it's kept private for obvious reasons. You can find a link to this diagram that I'm using here, as well as more details in our docs page. Now back to the demo. We have our group signature, and it's time to share it with others so that they can verify it and read the message. I could do this in any number of ways. Email it to people from a throwaway email account, post it to the blockchain anonymously, or put it as a response to a Google form or a Google Doc. Let me show you what it looks like when someone is given the verification link. When they click this link, they are taken to a page where the signature is pre-filled, but the message and public keys are blank. All they have to do now is click this verify button. The message, masked identity, and group parameters are decoded, and the ZK proof is verified. So let's talk about who can use this tool. If you've used SSH or GitHub before, you probably already have an SSH key pair, and that's all you need to use this tool. Additionally, you can grab someone else's public key, like I did here, just using GitHub by adding .keys to the end of the URL. This is why we chose RSA over other asymmetric encryption schemes. It is the most widely adopted one today and has great key distribution registries like GitHub, and therefore it's ready to integrate with all the existing Web 2 cryptography rails. So let's say you're interested and you want to use double blind to, for example, hold a survey for your GitHub organization. You want everyone in the org to be able to vote anonymously while preventing anyone from voting twice. All you need to do is grab the public keys of every member of the organization and input it into the app. Then share a link to the pre-filled signature generation form like this one. Your organization members will need to first authenticate by running this terminal command and pasting the signature into the box. Then they'll be ready to sign, and all they have to do is input the message and click sign. All the signatures you collect this way can be verified and shared in a decentralized and transparent way, making for a trustless survey process that all participants can help validate. You can also use this to power other authenticated but anonymous communication systems like community-gated message boards, whistleblower hotlines, or feedback forms. Of course, this is just the beginning, and there are infinitely more possibilities, both on and off-chain. To close, I wanted to share a somewhat sobering thought. Like any technological innovation, ZK RSA group signatures can be used in both good and bad ways. For example, the fact that you can be included as a member of someone else's group without your consent can be scary. And we were thinking hard about the affordances of this tech. So if you have any thoughts on the matter, we would love to hear from you. You can try out the app at double-blind.xyz and contact us via GitHub or email. Thank you for listening.
Yeah, so that's double blind. Oh, does this work? Okay, cool. Yeah, and just to summarize, we have RSA signature verification in Circom and about 300K constraints for GOT16. We're building out infrastructure for building and serving accumulator routes, and you can find the group signature utility at double-blind.xyz. And if folks are interested in following up, I can share Stephen and Andrew's contact info after the talk. Now I will turn it over to Yi, who will be talking about ZK pairing.
Okay, so as Ryan mentioned, I'm going to present our work on implementing different types of elliptic curve pairings, as well as BLS signature verification in Circom in GOT16. And I should mention that this project was really spearheaded by Jonathan Wang and Vincent Wang, who unfortunately can't be here today. So to summarize, we've implemented pairings on the curve BLS 12381, which is the curve used in ETH2 for BLS signatures. So we have implementations of the optimal 8 pairing in a little over 11 million constraints, and the BLS signature verification in the case where the pub key is in G1 and about 19 million constraints. So to give a little bit more detail on what that means cryptographically, to verify a BLS signature, you have to compute a single pairing check, namely that the pairing of a base point G with your signature is equal to the pairing of the public key associated with the signature and a hash of the message. So I'm going to give a brief demo to concretely verify this for a specific signature taken from the ETH2 beacon chain a couple days ago. So what we're going to do is we're going to take the signature of this validator on a block, which you can look up the details of on beacon chain. Unfortunately, the demo takes a bit of time, so I'm going to X out of all these commands. But what we're first going to do is look at the input. We have an encoded version of the pub key, the signature, and the message hash for this block. What we now do is generate the witness taking in this input. Let's imagine that 2 or 3 minutes pass and the witness has been generated. Then we're going to run the prover. Again, imagine maybe 1 minute passes and it generates. And if you believe me that I didn't just fake those last 2 steps, in about 1 second, you'll see that the proof verified. Okay, now back to the presentation. If you have more time, you can try this for yourself. Okay, so some benchmarks on what in principle happened there. We have 3 circuits. We have BLS verification, the optimal 8 pairing on the BLS 12381 curve, and the Tate pairing, which is not really used in production, but just a demo of a larger pairing. You can see the number of constraints is quite large. So these are pretty big circuits that require very beefy servers to run. The RAM constraint is over 100 gigabytes for all of these circuits. And as you can see, the witness generation and proving times are pretty long, even with a very beefy AWS machine. And last thing to mention is that here, even the proving key sizes are in the gigabytes, So that's definitely a constraint for applications. Okay, so let me just give you a brief overview of the challenges involved in implementing these circuits. So as a quick refresher, to implement the optimal 8 pairing, there's 2 steps. The answer for the pairing is this quantity f sub q of p. Doesn't really matter what it is, but it ends up being an element in a finite field. One has to first compute this quantity f and then raise it to a very large exponent, q to the 12 minus 1 over r. That's a little over 4,000 bit number. So to compute f sub q of p, we implemented Miller's algorithm within Circom. There's a couple challenges to resolve to do that. First, we need to use big integer arithmetic over a non-native field. And for that, we use similar techniques to what was used in Circom ECDSA. And we'll talk over those in detail during my workshop with Brian this afternoon. Secondly, we needed to do elliptic curve arithmetic over a field extension rather than the native field itself. So that introduces another layer of mostly software engineering complication. And finally, we needed to implement all the traditional cryptographic optimizations for Miller's algorithm, but within Circom. So again, this is a lot of engineering work. The second piece is what's called the final exponentiation. So that turns out to be a 4,316-bit exponentiation over the finite field extension FQ12. Q is a 381-bit prime. So again, in the traditional cryptography literature, there's a bunch of optimizations where first you can do exponentiation to Q using what's called the action of the Frobenius, which is very cheap, although a little bit complicated to implement in Circom. And second, we have to handle the remaining exponentiation by compressing to what's called a cyclotomic subgroup. So even in a traditional programming language like JavaScript or Python, this is quite complicated, but we ended up having to do this in Circom. You can look at our GitHub if you want to see the details. The last thing is to extend from optimal 8 pairing to actual BLS signature verification. There's one last step, which is hashing your message to an element of your elliptic curve group. It turns out, if you go read the spec, that this is a pretty complicated operation. I've drawn a little diagram of how it works. You start with your string, you do these 5 operations, each of which involve some elliptic curve math. In the end, you end up with a point in your elliptic curve group G2. We went to investigate how to do this on-chain, since we didn't want to snark it, and we found out that actually this is extremely expensive and uses a lot of gas. So for perhaps the first time I've ever experienced, we found that it was easier to just put this within Circom and put it in a snark. So that's what we've done, and in the code on our GitHub, you can see that we basically put the entire process of BLS verification after hashing to a finite field element within the snark. So you can check out our repo, which I just made public this morning, and we're going to have a more fully featured demo site up at zkxzk.xyz soon. Thanks, and Brian and I are happy to take any questions.
Yeah, I'm curious for the optimal 8 pairing on BLS 12381. Which optimizations and engineering tricks are transferable to BN 254, and or can we just kind of like use the same stuffs and just like on that curve as well?
Yes, although the current circuits are specific to BLS 12381, they can be changed to any other curve with some very minimal changes. So almost all of the optimizations will flow through directly. We just need to change the underlying elliptic curve library a little bit.
Yeah, just acting as a parrot here. My colleague was watching the stream and would like to ask a question. So my colleague believed that the main benefit of supporting pairing is to allow for recursive proofs. So do you have some measurements in number of constraints for verifying a proof recursively? Just curious.
That's next up on our roadmap, but we just haven't implemented it yet. So just for some context, to verify recursive proof, you have to do a pairing check that involves evaluating 4 pairings. And so we'll let you know when we have those benchmarks.
Hi. What approach are you using for non-native field operations?
We'll be discussing this more in our afternoon workshop, but the basic idea is that we break up the 200, or in the case of like ECDSA, where we're working with 256-bit numbers, we break it up into 64-bit limbs, and then we use a variety of intermediate representations that are a little bit more snark friendly to do most of the like big int operations like additions and multiplications. And then afterwards, we pull out of the intermediate representation into this standard representation of these elliptic curve points. So we'll talk a little bit more about those representations and why operations are easier in them later today.
Do you see a path towards breaking down the big circuit into several smaller circuits to make it more accessible to a smaller machine and maybe unlock distributed proving?
I think the constraint for that is the cost of recursive verification, which in our case is actually quite expensive. So I think for circuits that are even larger than the ones that we're talking about already, that could be a path forward. But for breaking these down, it's not clear to me that you can gain so much.
Yeah, at least one thing that this does is it establishes kind of an upper bound on the largest circuit you should ever have to prove, assuming that you have access to some sort of like, multiple machines or proving servers. And so you can imagine as this stuff gets better, like eventually we'll probably move to something more like Planck-like, and there's lots of circuit optimizations to be done. The proving libraries can presumably be optimized and hardware can presumably be optimized. So because this is like a generic non-native field implementation of pairing, it can sort of serve as like an upper bound on just like the biggest snark you'll ever need to do, hopefully.
Thank you. Kind of a follow-up question. So another benefit of pairing is one can build a universal dynamic accumulator, and I was wondering if there's any experimentation on that front. Thank you.
Again, that's something we're interested in doing, but we haven't gotten to it. So we'll let you know.
I had the impression that for cryptographic primitives, it's mostly kind of grinding and not so much using lots of memory and I/O, but you said 100 gig of RAM was required for this machine. So is it the case that for these big proofs, you do need a lot of like very fast, local, very near kind of memory?
I guess I'm not sure about the local memory, but the reason for the RAM usage is just that these circuits have a large number of constraints and a large number of inputs. And so the memory usage is basically determined by those in the all steps of Groth 16, so the proving, the key generation, and the circuit compilation.